In our lab, we examined sucrose concentration and optical rotation. The purpose of this lab was to use a 3D printer to construct a polarimeter, which would in turn demonstrate polarization. Light is the disturbance of electric and magnetic fields that travel in the form of a wave. These vibrations occur in numerous planes. More specifically, a light wave can vibrate up and down in the vertical plane, side to side in the horizontal plane, or in an intermediate direction. When these light waves are vibrating in more than one plane, it is known as unpolarized light. Unpolarized light can be turned into polarized light, which means that the light waves vibrations occur in the same plane. This process is known as polarization. When a solution is optically active, the molecules in the solution rotate the axis of polarization. These molecules in the solution cannot be superimposed on each other.
So here's our instrument. On the left side you can see our polarimeter case. The front holds the flashlight. The square hole is where we tape the horizontal fixed polarizer. And then in front of the circular holes, that's where we're going to put our protractor and rotatable polarizer. And then behind that is where we place the iPhone to take pictures. In the top right corner, it showcases the protractor with a hole for light to go in through and a little circles around it to put the rotating polarizer in. And the outside markings each mark 1 degree. The inside markings do 5 degrees. In the bottom right corner is our rotating polarizer. Basically, you just put it in, you attach it to the protractor and you can rotate it, and then like the arm kind of allows us to measure the angle, and basically we just attach a polarizer to it. So here's our assembled device. As you can see, the flashlight, light goes through the horizontal polarizer, through the cuvette of the optically active solution, and then through the rotating polarizer, and then the phone's at the other end ready to take a picture of it. So experimental design was like, we have a LED flashlight to use as our light source, and we have 6 cuvettes of varying concentrations of sucrose, and we use 0 grams per milliliter, 0.4, 0.8, 1.2, 1.6, and 2.0.
Here is our polarimeter, and the way it works is by having a light source, which for us came in the form of an LED flashlight. And this light source projects light through a horizontal polarizer, which you can see right here. This polarizer horizontally polarizes the light, which then passes through an optically active sucrose solution. This optically rotates the light and changes the axis of polarization. We then use this iPhone, which is iPhone SE, to take pictures of the light intensity. We use those values along with the angles of rotation, the rotational polarizer, to determine the new axis of polarization.
So our procedure, basically we set the rotating polarizer to 0 degrees, and so we would just put the cuvettes, each cuvette in the slot. So like basically we start off by putting the 0 grams per milliliter concentration sucrose water, and then we'll put it in the slot, take a picture, and then go to the 0.4, take a picture, and just do that for each concentration. Then we rotated the polarizer by 2 degrees and then took pictures for each polarizer again, and we did this for 60 degrees of rotation. Basically, we were trying to find which angle has the maximum intensity because that would indicate which the angle of polarization after, or the angle of polarization of the light after exiting the cuvette of the optically active solution. So measuring the intensity, we had Python code that basically measures the RGB channels for every pixel. And so as you can see, the I represents the intensity, and it basically just adds the red channel, the green channel, the blue channel, and divides it by the number of channels, which is 3. And we kept the size of the pictures constant at 3024 by 4032 pixels by keeping the iPhone camera all the way zoomed out. At the bottom, you can see an example. Here's one of our pictures that we took. And basically, the Python code will just go through each pixel of that and just calculate the intensity. So here's our data analysis for the 0 grams per milliliter. Basically, on the x-axis is the rotation of the polarizer, and on the y-axis is the light intensity. And you'll notice why we stopped at 60 degrees of rotation, because it's kind of obvious that there's just no way, like, that we passed the maximum of it. And so also we found the maximum at 18 degrees. For 0.4 grams per milliliter, the maximum was at 22 degrees. For 0.8, it was 24 degrees. For 1.2 grams per milliliter, it was 28 degrees. For 1.6 grams per milliliter, it was 28 degrees. And for 2.0 grams per milliliter, it was 32 degrees. So for calibration, you'll notice that at concentration 0 grams per milliliter, the maximum is at 18 degrees, which means our horizontal polarizer didn't exactly completely horizontally polarize the light at exactly 0 degrees, but rather at 18 degrees, because there's no optically active molecules in that cuvette. So basically, to find the optical rotation, we found the degrees at maximum intensities and subtracted them by 18, and also defined the variance in our measurements of light intensity. Basically just took 10 pictures at constant angle and concentration, and our standard deviation of those was 2.94 times 10 to the 7th 8 bits per channel, which is actually smaller than it seems. Here's our linear regression of optical rotation versus concentration. As you know, we are examining the relationship between the degree of optical rotation versus concentration. So as you see, our slope is 6.6 plus or minus 0.6 degrees of optical rotation for every gram per milliliter of concentration of sucrose. And so up top is like the polarimetry equation, where A represents the degree of optical rotation, C represents the concentration, and A divided by C is basically the slope of our regression line, and beta is the specific optical rotation, and for sucrose that's 66.47, and L represents the distance that the light travels through the optically active solution. And so since the inside of the cuvette was 0.09 decimeters, that's what L is. And so by using this formula, the expected slope should actually be 6 plus or minus 0.3 degrees times milliliters over grams. And so that means our percent error is about 10%. What this means is we're kind of actually successful in using polarization to show the optical activity property of sucrose. We examined the relationship between concentration and degree of optical rotation, and we found it to be 6 degrees for every gram per milliliter of sucrose. And it is a very cheap way of doing this. We only spent about like $13. And so recommendations for next experiments is a bigger protractor for smaller angle increments. We could only do it in 1 degree increments, or we only could measure in 1 degree increments, and it'd be better if we could measure in the tenths of degrees, and we could like take more data points, and also making the experiment more time efficient. It took us about 6 hours to collect our data, and so while we didn't really notice any decreases in intensity of the flashlight, it very well could have happened that the intensity could have decreased a little bit over that time due to the depleting flashlight battery.